what we're going to be looking into this week is how we can actually go through this graph and figure out different paths through the graphs, right? Because it's one thing to have a graph represented, but it's another problem to actually be able to find, for example, the shortest way to get somewhere, right? So this is kind of what Google Maps is doing, right? But we're going to start off really simple. We're just going to go with an undirected, unweighted graph. So it's going to be just literally the most simplest way possible. And the first thing we're going to look at is something called BFS. So this is called the breadth first search. All right, and there's a really closely related sibling here called DFS, which is depth first search, and we're going to be looking at that next week. As you can see, what it does is we'll first search through all the nodes that are within the same depth before moving on to the next level. So as you can see here, first it goes from 1, then it goes from 2, 3, 4, and then it goes 5, 6, 7, 8, and then it goes 8, 9, 9 and 10. So the way we can kind of implement this is using something called a queue. So adjacent nodes are added, which is kind of like a list. So you can think of a queue as a list. However, adjacent nodes, so any kind of nodes that are connected directly to this node, are added to the back of the queue, while the next node that you're going to go to is determined by looking at the front of the queue. So because of this, we can guarantee that the first path we find through BFS is going to be the shortest path possible. So, right, if we're always going like completely, we're going through every single level the same, the moment that we hit a node, that is going to be the shortest path possible that we can take to get from some node to another node. Well, one of the kind of the trademark questions that you'll see with a BFS is going to be finding the shortest path, or how long is the shortest path to find something, right? Generally with DFS and BFS, when you're looking at an unweighted, undirected graph, even a directed graph, there really isn't too big of a difference if you aren't given any other information. You can use generally either and you'll get the same result. However, given more information, you can make a more informed choice. So for example, if a question asks you, what is the shortest way possible? You want to use BFS, because what DFS does is it doesn't actually guarantee that you arrive at the shortest one first, but BFS does. That's the general way that BFS is implemented. Now, what I want to quickly go over is a queue versus a stack. So I mentioned that BFS operates as a queue. So what this means is that, for example, I have a, let's just put lines here for the nodes, okay? So, or dots, all right? So we're going to call this the head. So this is the head of the queue. So what that means is the algorithm always looks at the node at the head. What happens in a queue is that new nodes, or new anything really, are added to the back, right? So if I'm going to be searching to a next node, I'm going to add it over here. And then after, when the algorithm is looking for things, it's going to take it from the beginning. So this is very similar to how a line works, right? So for example, when you're, in the cafeteria, or if you were in the cafeteria last year, right? Unless you're a total jerk, what you do is you stand at the back of the line. And then after, the cafeteria person serves you from the front of the line, right? So we can call this first in, first out. The node that, or anything that goes in first, is also going to be the first one that comes out. However, there is a different one, right? So now, because so this is the queue. Another thing that we might use that you'll encounter next week with DFS is something called a stack. So this is going to be, let's call this a queue. All right. Whoops, this is not a brush. This is a brush. This is a queue. And another way that we can do this is using something called a stack. So we're going to use the same kind of analogy here. We're going to have the head right here. However, whenever we add things, we are adding it to the front of the stack. So let's say we have node 1 here. And then after we... it depends. So yes, generally you do check emails in a stack. However, like for example, I have my emails actually ordered the opposite way, so that the ones that have been unread for the longest I see first. So it just depends on your settings and everything. So right, we not only does the algorithm look for nodes at the front, however, we are also taking things from we're also putting things in at the front. So let's say we add another node here. It's going to go in the front here, and then it's going to go over here. All right, so this is very similar to, like, for example, yes, an email checking, for example, right? At the top of your inbox, that's still going to be the latest email if you can have it configured that way. Another thing that I've seen a lot is talking about plates, right? If you're at like an all-you-can-eat restaurant or something, that stack of plates, when they bring new ones in, they always put the new ones on top, and you also grab your plates from the top, right? Unless you want to risk, knocking the whole thing over and taking it from the bottom. Everyone understands that. So then let's jump right into actually implementing this in Python, right? So here's our graph that we're going to be using. So as we can see here, this is just a pretty simple graph actually. And we're going to be looking to make a program to find the length of the shortest path between the two nodes 0 and 5 here. So this is 0 over here, and this is 5 over here. Okay, and in this example, we're just going to be representing that with an adjacency list. And as well, just to keep things simple, this is going to be an unweighted and undirected graph as well. Now, we can see there are quite a few ways to get from 0 to 5, right? Not doubling back on yourself. So you can go 0 to 5. You can also go 0, 4, 6, 7, etc., etc. So yeah, let's figure out how to do this in Python. Now, the first thing we need to do is actually make that representation of the graph. So in this case, I started the node IDs with 0 so that we don't need to worry about our adjacency list with the indexes getting all weird. So the very first thing is, how about this? Why don't you guys, without looking at the lesson plan, why don't you guys build an adjacency list based on this graph? Okay, Arfa, thank you for that. Let's go ahead and just take a look at this one. So, as if you guys remember, an adjacency list lists all of the adjacent nodes in a graph. So let's look. So we have 0. At 0, it's going to be 1, 2, 4. So 1, 2, and 4. Okay. 1 is 0, 3, 6. So 1, 0, 3. Sorry, 4. Yeah, 0, 3, 4. That's correct. Okay. And we have 2 is 0, 5. So 2, 0, 5. Yep. And we have 3 is going to be 1. That is correct. Okay. And then after 4 is going to be 0, 1, 6. So 0, 1, 6. That is correct. All right. 5 is going to be 2, 7. Yep, that's correct. Okay. 6 is going to be 4, 7. So 4, 7. Yep, that's correct. And then after 7 is going to be 6, 5. All right, and that is correct as well. So this is a correct. This is the correct representation of the graph. So we can just go down here. No, it looks like I missed a 1 here. So this should be, these two should match. Again, remember that the order doesn't matter. So like this could be like 7, 4 or 4, 7. That doesn't really matter. So the first thing what we want to do here is we are going to copy this implementation. Now, generally, this will be given as input in a question, right? So it might say, okay, it'll give you like, it'll give you edges. So for example, like 1, 4, and then 2, 5, and you'll have to build this yourself. But in this case, we're just, as this is an example, we're just going to hard code it in our code. So the very first thing we're going to do here, it's actually not really required if you don't want to do it, and that is to import Q. So this is a specialized data structure that is a queue and provides some helper methods that we won't really use too much. So if you just want to use a list, that's totally fine. Again, just make sure you're implementing the correct things, right? You're just adding it, you're adding it back and just removing from the front, and you should be good. Another thing that we're going to hard code is our start and destination. We're going to be starting at node 0. So let's set start to equal 0. And then we're going to have a destination of node 5. So we're going to have that as 5. Now, again, remember that the kind of the thing that BFS revolves around is a queue. So we're going to create it. Generally, I call my queue queue. And after we initialize it this way. Now, this could also be a list. And it'll also work about the same. Now, the first thing we're going to do is actually put into our queue the place we want to start, right? Because that's where our algorithm is going to be starting. We're going to say q.put, and we're going to put in a tuple here. And the reason we're going to be doing that is because the question is asking us for how far we've traveled. So we need to keep track of that as well. So we're just put a tuple here. We're going to say start. And then our second index is going to be how long we've traveled. So far we have traveled 0. So we'll just put it there. And then another thing we need to put here is a visited list. Now, remember how in the beginning I said there are many ways for us to go through this graph without doubling back? That is something we do need to be careful about, right? Because if we can double back, then essentially we can have unlimited methods of going through this graph. We can go 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, 7, 5, right? Because we're trying to find the fastest way, obviously we don't want to be doubling back. And in fact, this will cause an infinite loop to happen. So we are going to be keeping track of which indexes we've already traveled to by using a visited list. Now, here we're just going to be using some list comprehension to fill it with false, because so far we haven't actually visited any of any nodes on this graph yet. And now this is going to be the fun part where we're actually going to be doing the search. So we're going to say while q. So what this means is while q is not empty. That's one thing, is that there are some things in Python that can aren't exactly true or false. However, you can evaluate them as true or false. For example, 0 can also be evaluated to false, and also an empty list or a string of no length also equals false, right? So this is just to reduce the amount of code we're saying. Hey guys, I just want to make a quick note here. So I mistakenly told you that you can use q like this to check if it's empty. However, that behavior is not actually present. That's actually with a list. So I apologize for that. If you want to check, so you can do this with a list, it'll be fine. But if you want to use a queue, you need to say while not queue.empty. Now the first thing we're going to do, remember, in a queue we are getting from the beginning. So we're going to say c.equal. So this is current node that we're working with equals q.get. So what this will do is this will return the thing that's currently at the front of the queue and also remove it. Next, we're going to mark this node as being visited, right? Remember that our node number is the first index of this tuple here. We're going to set it to true, which means that we have visited it. And next, we're going to check if we've actually arrived at our destination, right? So we're going to say if the index of the current node that we're at is equal to the destination, we can go ahead and just print out how far we have traveled and break out of the loop. Now, if this doesn't happen, we actually now want to move on to the next layer, right? So this can be accomplished with a loop here. We're just going to say for next in G. So we're going for the graph, and we're going to look up all of the adjacent nodes from the current node. All right, and then we're going to make sure, we're going to check if it's been visited, right? Because we don't want to be doubling back. We're going to say if it has not been visited, we're going to put it into the queue. And we're also going to increase the amount that we have traveled. Okay. So this is this is a very generic BFS implementation, right? You might need to change this, right? Very rarely will you get a question that's going to ask exactly for this. You generally do need to make some tweaks, but this is a general implementation. So q equals q.q, we're just creating a new queue. So this would be the same as, for example, you can also create a list this way, right? So in this case, we're just calling it, the structure is called a queue. However, we're importing from queue, so we need to prefix that with q.q. So this is part of the 7-week challenge in 2016. So there's a bit of a storyline, but essentially what you're looking for is there are n houses in Shahir's neighborhood, and there are m roads that connect those n houses. So the houses are the nodes, and after the roads are the edges. So each road connects 2 houses, and all roads can be traveled down both directions. So so now we know it's an undirected graph, and each house is distinctly numbered and identified by a number in the range 1 to n. So in this case, we know that the node numbers are ranging from 1 to n instead of 0. So that's something we'll need to pay attention to. And it tells you that Shahir lives in house A, his date lives in house B, and it's asking you if there is some path from A to B. First, our input specification. It gives us the first 4 integers. So the first one is the number of houses. Then M is going to be the number of roads. And then after A is going to be where he lives. And then after B is going to be where his date lives. The biggest thing I guess we need to discuss is how we're going to take input. This is one thing that I should actually mention here is Python's input is actually a bit slow. So thank you, Alan, for bringing that up actually. Once you get into the thousands and the tens of thousands of lines, your input can actually be, because it still takes constant time, right? There's still some time that's taken. Your input can actually end up putting you over a TLE, especially if you're right on the edge. So generally when we see, 2,000, 3,000, 10,000, 50,000 lines of potential input, as we can see here, we can have potentially up to around 2,000 lines of input. We should actually be moving to Python fast input. So the way we can do that is we can do this. Just import sys, and we can just literally change input to sys.stdin.readline. So this has basically the same behavior as input, so you should be able to treat it very similarly, but they're just it's mostly the same, so you shouldn't need to worry about it. All right, so this allows us to take faster input so that our input is not where our program is taking the most time. Now, next, I think, Alan, you made an array. I did it differently, which is totally fine. I just mapped these all out so that I could use them independently as variables. All right. So the next thing we need to do is to figure out how we're going to represent our graph. I looked through a couple of your submissions. It looked like a few of you were using an adjacency list, and a couple of you were actually just storing all the edges as an edge list. Now, in this scenario where there are 2,000 edges, I would highly suggest that you don't use an edge list, just because you can't actually directly go from one node to another. You actually need to iterate through that edge list every single time. And we know that the time limit here is actually 1 second here, right? And Python can do around 1 million operations a second. So that can end up where you can only do around 500 of these checks before you run out of time. Potentially can work. But that's a worst case scenario. You can go grossly over time. You can, worst case where you're actually going through every single road, you can take up to 4 seconds doing that. So I would not recommend using an edge list. In this case, we're just going to use an adjacency list. And to be honest, that's what I normally solve it with, either an adjacency list or an adjacency matrix. Those are generally what you would use. But of course, there are definitely cases for an edge list. So don't just immediately discount that. In this case, we're just going to first fill this graph. It's just a habit. You actually don't need to do this. You can actually just iterate and then after add it later, but it's not too big of a deal. So now we're going to go through every single one of these. And now we are going to get the X and the Y. So that's going to be the starting point of the road and the ending point. And again, we're going to map that. So I really like to use map because it gives, instead of having to remember which index you're storing it in the tuple or the list, you can directly use that variable name. So it's a little more readable and it just helps you immediately see what value you're using. So next, what we're going to do is we're going to now add it to our adjacency list. Because remember that our numbers actually are starting at 1 this time. So we need to actually subtract 1. Otherwise, like when we refer to something in our list, right? Node 1 is actually going to be equal to node 0. Now, if you were to actually append this, if you were to just create this and append it as you go, that would also work, but it's a little more tricky. That's why I would just always fill it with empty lists beforehand. But if you are just appending lists, you will not have this problem, but you will have the problem later on when you're trying to access it. You might get an index out of range error. Now we're just going to go ahead and append that this one has a connection to here. And then after this is reciprocal because the roads are bidirectional. Next is actually going to be where we're going to search. So we're going to create a queue here, and then we're going to put in the first number. Now remember, we have subtracted 1 from every single node number. So we actually also need to do that for this first initial value, right? Because we haven't processed this value. This is directly from the judge, and the judge's node numbers start at 1. So we need to subtract 1 to make sure that aligns with the numbers we're using. And now we're going to create a visited array, or a visited list, sorry. And that's going to be that. I think that's pretty straightforward. And then we're going to also keep track of if we have found, yes, you will have to import queue. Yes, sorry about that. Thank you for reminding me. Now we can just simply, this is a very similar to the example we had. So we're just going to say, while it's not empty, we're going to get the current thing. We're going to set it to being visited. Then if the location we're currently at is -1 of B, remember again, B we also have in process, so it's going to be one larger than all the numbers that we have. We can just say we have found it, and then after we can just go ahead and break. Now if we haven't found it, we're just going to try to go to all the next nodes if they're not visited yet. All right, and then at the very end, we're just going to say if it's found. We can go ahead and print go Shahir. No, that's not how you spell it. Shahir. Else, we're going to print no Shahir. Okay, so this is a very straightforward question. No, nothing really fancy. This will get you the right answer. Quick warning here, to make sure that you're using some sort of way that you can access whether you visited it in constant time. Especially with BFS, this is very easy. Again, I would just use a visited list, and then you'll be able to access it very quickly. Thank you guys for coming out here. I know this is a pretty slow lesson, but again, I really want you guys to make sure that you understand this because everything's just going to build off of this. I have posted a whole bunch of questions, 6 other questions that you can do. So, one for every single day this week. So please, I would encourage you to try them all. Some of them are a little tougher than the others. I would say at the very beginning, it might take around an hour and a half to solve them, but by the end, you should be able to solve them in around 30 to 45 minutes. Again, if you have any questions, you can always just ask in junior help. Anyone potentially can help you out. But yeah, so again, also lesson plans are available in the drive, and I will be throwing this lesson up on YouTube later in the week as well. All right, so thank you guys for coming out again, and I hope to see you guys next week. We're going to be starting DFS, which is a different way of searching through a graph.